Okay, welcome to the lecture for MRI the Basics, Chapter 17, Scan Parameters and Image Optimization. So our goals for this chapter, which was relatively short like the previous, but is some fundamental and really powerful concept, the concept of signal-to-noise ratio, or SNR. And so we're going to define what this is. We're going to go through how to calculate expected changes in SNR based on sequence parameters. And then we're also going to go into 3D imaging, so 3D FT specifically. And then in class session, we'll go over a little bit more closely the definitions of scan coverage. Okay, so first we want to define the signal-to-noise ratio, commonly referred to as SNR, which is, as the name implies, is the ratio of the signal S. This comes from the precession of our transverse magnetization. And this ratio on the denominator is the noise. And the noise in MRI is the coming from the random motion of charged particles, for example, ions, within the subject. So just the random motion within your body if you're in the MRI scanner. We can also have this random motion within the electronics, so our RF coils and amplifiers. Note that if we, in typical human imaging systems that are well designed, the noise from the electronics is much smaller than actually the noise coming from the body of the subject. And the term here we use to define the noise is sigma, for the standard deviation of the noise. So we might typically illustrate it, this concept, as we have some signal that we're trying to measure here. This is the, in our case, the transverse magnetization. But when we create an image, we're going to have some noise that is going to be superimposed upon this signal. So the actual measurement is not one or the other of these, but is the combination of these two together. So we get this noisy reproduction of our underlying transverse magnetization. And again, the sigma, the standard deviation, can be calculated based on these fluctuations, or it's one standard deviation of this noise value. Okay, and in MRI, there's three factors that contribute to the signal-to-noise ratio. And number one is the sequence contrast. So for example, and that's represented by this term here. For example, we know that if we change, if we have different, for different choice of TE and TR, then this will change the signal level depending on the T1 and T2, and also M0, the equilibrium magnetization. So we dump all that into this F term at the beginning here that we've covered already. Then the two other important terms that we're adding here, one is the voxel size. So that are these three terms here. So making that explicit here, our spatial resolution in X and Y, and our spatial resolution, sometimes this is our slice thickness in the third dimension. And you see here we're actually looking at a voxel volume, the product of all three of these. And then finally, this last term here, the square root of the T mes as it's abbreviated, is the measurement time, or the total measurement time. So how much time we spent acquiring our data. And now a common confusion is to mix this up with the total scan time. These are not necessarily the same. This is the time that we have that DAQ actually on during the experiment. So we're going to go through these factors one by one. First, the sequence contrast. So here we're looking at this term here. And this is the things that we've covered before. For example, when we have our 90-degree flip angles, we can get a relationship of 1 to the E minus TR over T1, and we have our T2 component there. We also have the relationship for inversion recovery, or what we cover in a little bit here is the, the relationship including non-90-degree flip angles. That's the gradient echo equation at the bottom. And these are our sequence contrast relationships that do, of course, modulate our signal amplitude. Next, we have our voxel size. It's here. And the intuition here is that the signal in our voxel is proportional to the total number of spins, or the total net magnetization that we have within a voxel. So we create our, say, our net magnetization in our imaging voxel. And the picture, we've used before, that the signal in the voxel is the sum, right, of these 4 individual transverse magnetizations. And that's basically how it works. This relationship does assume that there's homogeneity within a voxel, so there's not a lot of variability there. That's a pretty reasonable assumption in most cases. And so as an example of what could happen, let's say when this original case here, we have our resolution of delta x, delta y, delta z. Oops. Let's say we went to a case where we're actually going to chop up a voxel. We're going to say we have a new resolution, delta y hat is half of what it was before. Similar for the spatial resolution in x, and we'll keep the z resolution the same. What's going to happen? We'll still have the same underlying net magnetization, but now the signal, for example, within one of these voxels is simply, in this simplified illustration here, it's just going to be the spins that are in the quarter of that volume, and since we're summing these together, this is a linear relationship. So the expected signal from the voxel in this case would be a quarter of the original example on the left, because we divided our entire voxel up into 4 different parts. Okay, and the final term there is our measurement time, abbreviated here. And this concept is maybe going to be a little more complex to explain, but the basic intuition here is that noise versus a random process. And so if we make different measurements, the noise is constantly changing. It's going to change between every different measurement. And so it's going to be what we call incoherent, and it's going to progressively cancel out throughout our measurements. Whereas the signals, so the transverse magnetization that we actually want to measure, is going to be coherent measurement to measurement. So these signals will stay the same, while the noise will begin to progressively cancel out. So Let's see if I can give you a nice illustration of this here. So say we took two measurements of our object. We already have a measurement 1, which is going to be our signal, plus a noise, but this is going to be noise 1. And what I mean by the point above there is that if we take a second measurement, and hopefully I'm drawing it somewhat random, is that if we take another measurement, it's going to contain the same signal, but the noise, I'm going to denote that as noise 2 because the noise is actually changing between these two measurements. So let's go ahead. You can look at this as the effective measurement time of, in this model, we're going to add these two together. And what are we going to get here? So we're going to get, and it's a little hard to illustrate, but we'll get some measurement that's going to be, it's going to have 2 times our signal, but it's going to have the addition of these 2 different noise patterns here. Great. And if I extract this out into the signal, if we can do that, and we get a coherent averaging of the underlying signal. And then if we could extract the noise here, this would be N1 plus N2. Can use some statistical theory to determine what the standard deviation is going to be in this case. So let's go back here and illustrate, well, this has some standard deviation of the noise, sigma. The standard deviation of the noise is not changing measurement to measurement. But what statistical theory will tell us is that the standard deviation when we add these two noises together doesn't scale linearly, it scales as the square root. So it's going to scale as the square root of the standard deviation. Then taken together, what this tells us is that, so here we have an SNR that was, and let's say this SNR of 1 just from one measurement. So from either of these two, we have the SNR of a single measurement, but in our SNR2, meaning it's the two measurements added together, we're going to get a signal to noise that is, the signal again adds coherently. The standard deviation of the noise does not add coherently, it adds with the square root term, and this means that ultimately we get a square root of 2 improvement in the signal to noise by averaging our measurements together. And this is a result that comes from statistical theory and the intuition as I explained above. Now the reason in the top equation here for SNR is that there's a square root in this measurement time is the same reason that there's a square root in this example here. Okay, shifting gears a little bit, I want to talk about how to perform 3D or 3D FT imaging. And the concept basically is very simple. Is that what we're going to do is we're going to add an additional dimension of phase encoding. And we're going to do now along the slice direction. So if we look at this from the case-based perspective, let's say we're going to have now 2 dimensions of phase encoding. We're going to do one step where we're going to do a positive Y and positive Z phase encode. So we're going to end up, in this case, where are we? Positive Y, positive Z. We're going to go out to some location here. And the other 2, we're still doing a negative kx, then a readout kx. And if we look, it's a little hard to visualize, but if we look at this in terms of the 3D volume, what we've just done here is we've gone up to positive and ky, positive and kz, and I've gotten across the frequency encoding dimension. And what we've done here is we're still using the same general case-based relationship. Just noting that before we'd only used x and y, but now we can take advantage of this vector form of this, and in fact compute a kz as well. Now we're going to, and I'll just illustrate some extreme examples. You might do a negative GZ gradient, a positive GY. So that's going to look like going out to this quadrant case space, or it's going to be sort of in the 3D volume at the top here. It's kind of going to be back behind. And if I draw out the coverage here, and what we're going to do is we're going to be able to fill in this 3D volume in K-space. Let's combine a positive GZ with a negative GY. So then we're going to positive in KZ, negative in KY, positive KZ, and now we're getting to negative in KY. Okay, so that covering up in this corner of our 3-dimensional matrix of K-space. And then let's say we did both negative. Then we're going to these negative phase encoding steps and start to cover this corner of our 3D K-space volume. So once we have this 3D K-space data, we simply reconstruct no longer with a 2D Fourier transform as in 2D FT imaging, but with a 3D Fourier transform. And here's a couple notably sort of very high-end examples of 3D imaging, but the key thing you can see is these are sliding through the slices, is this data is really contiguous. That's another advantage of 3D imaging, is that there's not individual slices that chunked up, that the data is truly sort of continuous in this dimension. And you can see at the top of the brain, this is like one of the highest resolutions MRI you might ever see, done in 100 hours of scanning, so not practically very feasible, but just these absolutely beautiful depictions of the brain. And this is an example. It's not only 3D imaging, it's also fast time-resolved imaging using some a lot of tricks in the image reconstruction process, but you can visualize, this whole upper torso of this, it's a kid of this child, and look at the contrast agent that's actually injected here. Okay. Finally, I just want to comment briefly that what are a couple of the key differences between 2D and 3D FT imaging. One is going to be the scan time. So as we know, for 2D imaging, we multiply the TR times the number of phase encodings, and now we've introduced this concept of we can do signal averaging as well to increase the SNR or NEX. Whereas in the 3D FT case, we now have 2 dimensions in phase encoding we have to loop through. So it's TR times the number of phase encodings in the first dimension times the number of phase encodings in the second dimension. On top of that, multiplied by any signal averaging. And generally, the primary use cases for 2D FT are going to be our longer TR contrast, so T2 and proton density weighting, where we're going to do a single slice, and then during the downtime of the long TR, the dead time, we're going to acquire additional slices. Whereas with 3D FT, we're going to use this typically in short TR pulse sequences where we don't have as much of that downtime, but we can really do short TRs but acquire a lot of different phase encodes. So actually, even though there's an extra term in this scan time, we'll use shorter TRs generally to keep the scan time reasonable. Okay, so I'm just refreshing the learning goals. Talked a lot about signal to noise ratio, and I'll go over a bunch of examples in class of that, as well as continuing to elaborate on the 3D FT imaging sequence, and we'll go over the final learning goal in class. Okay, thank you very much.